Okay, so let me present this set of exercises. These all relate to hidden Markov models, and the bullets here present the key problems involved in solving hidden Markov models. The first problem is, what is the probability that a model generated a sequence of observations? So you're given some sequence of observations, and you're also given the model. Now remember what A, B, and pi mean. A is the transition matrix on the hidden states. B relates the hidden states to the observations. And pi is the initial probability distribution. Now these three quantities, this matrix A, this matrix B, and the vector pi, uniquely represent the model. Now when you run the model, because there's randomness, every time you run the model, you'll get a different sequence of observations. And we want the probability that this particular sequence of observations will be observed. So he says P of O given lambda means we're given this model, these are our assumptions, and we want the probability of observing this sequence. Okay, we'll skip these two for now because today we're just going to look at this first one. Right? So you can see that we need to specify A, B, and pi. Right? Now these all work on a set of states. Right? You're talking about transitions between states. So this is kind of a diagram of the case where you have 9 states. So we're going to have 9 states. I'm arranging them in a circle. I numbered them from 0 to 8 because when you do Python, indexing starts from 0. And you can see 0 can go to 1 or 8. 1 can go to 0 or 8. Right? That's what the arrows are showing. The arrows are showing possible transitions. All right? So we need to specify this mathematically and computationally so that we can figure out how the model behaves and simulate it. All right? So this first bullet asks you to create the matrix A given certain parameters. All right, so we're assuming n states, and of course we can make n be a particular number. Okay, so the function AMX is a Python function, and it has one input that we call pvec. Now pvec is not a probability vector. The components of pvec do not sum to 1. What pvec actually is the vector of left jumping probabilities. Okay, it's either left jumping or right jumping. We'll figure out when we get down here. All right, so it's a vector that we can use to create this matrix A. All right. Now here it says for testing purposes you may let pvec be the vector with all entries 1/2. So pvec has the same length as one side of the matrix. All right, and one side of the matrix A corresponds to the number of states. So as I said here, this shows the case where you have n equals 9. All right. Now the state transition matrix is actually going to be a sparse matrix. Most of the entries are 0. What this is saying is that if I'm at state n minus 1, then the probability of going to, if I'm at state 0, the probability of going to state n minus 1 is pvec of 0. So if I'm at state 0, and the probability of going to this state here, which is 8 in this case, is pvec of 0. So I said left jump probabilities. This pvec actually is giving me the right jump probabilities. Probability of 0 to 8 is pvec 0. The probability of going from n to n minus 1, so for instance for any n, in this case n equals 3, probably going from 3 to 2 is pvec of 3. All right, so you'll have those probabilities, and you'll have the probabilities of the left jump is just the complement probability of the right jump. Right. So in the case that I'm asking you to do, if pvec is 1/2 and the probability of going from 0 to 8 is 1/2, the probability of going from 0 to 1 is also 1/2. Now, if you create A correctly, you can see here that each row has 2 entries. So each row will have 2 entries. And these two entries will sum to 1, right? So this is the row, this is the column, right? Right. So notice here that these 2 indices, the n refers to the current state, the n minus 1 state refers to the next state. So what that means is that when we run this Markov chain, we will represent the probabilities of states as a row vector, and we will multiply on the right by a, right? Because this goes from n, this is the current state, this is the next state. So as I say down here, this describes a process where the system either hops one state to the left or to the right. And this could be the location of a person or the location of some kind of robot or something like that. But it's describing a location that changes over time, and you can think of it as going around a circle. All right. Now, what is OT? OT is what you observe. Now, your observations are not accurate. You may not accurately see what state the process is actually in. So what this says, if the state is actually n, the state will be measured in one of these states. So, for instance, if m is equal to 1, and the state is actually 2, then the measurement may determine the state to be 1, 2, or 3. All right, so the measurement is inaccurate. Maybe you're looking at this system from a distance and you don't have enough resolution to determine the exact location. Now, this specification is relating the true state and the observation. So this information allows us to specify the matrix B. Now, the matrix B is the probability that you observe K given that the true state is J. Now, that's exactly what you have here. Probability that you observe this value given this value, given Qt equals n. And you can see that this depends on capital N and capital M. So you're to use this information to create this matrix B mix, right? And that will be encapsulated in this function bmixFun. Now you can check your work here also. If this is done correctly, then the rows of this matrix should add to 1. Because for any given actual state, you're going to observe one of several choices of observed states, and the possible observations have probabilities that add to 1. Okay, so that's number 2. Number 3, write a function qvecFun with 3 inputs. First is the transition matrix, which you would have created with amexFun. The next is the starting state. Now Q0 is going to be an input, and it will be a number from 0 to n minus 1. So we have one particular fixed determinate starting state, and the number of hops t. The output of qvecFun is a vector qvec of randomly generated hidden states produced using the transition probabilities in Amex. So I should be clear here. The vector qvec does not include Q0. So the first entry of qvec would be the state that Q0 moves to. Now you can tell if you did it right, because if you did it correctly, the vector qvec should have the same length as t. Right? Each hop produces one element of qvec, and we do not include the starting state as one of those elements. Okay, so number 4 built on number 3. Write a function ovecFun with 2 inputs, the observation matrix bmix, which you created in 2, and a vector qvec of hidden states. The function will output a vector of observations ovec that are randomly generated based on the vector of hidden states qvec and the probabilities of the observation matrix bmix. All right, so ovec will be a vector of the same length as qvec. These will be the hidden states. This will be one possible set of observed states. Right? Okay, using the above functions, you can write several simulation codes. Here we're going to take one particular model with n equals 30, 30 possible states, m equals 2, and the starting state is 15. Let p-vec be a constant vector with all entries uniformly chosen in this interval, 0.499 and 0.501. All right, so the jumping probabilities are almost evenly balanced, but not quite. And in this case, the p-vec is not the same for each state. Right? It differs for the different states. Right? So they're randomly chosen. So so you'll get a different answer each time you do this, because you'll get a different set of random numbers here for your transition probabilities. So what you want to do is generate 1,000 sequences of hidden states and observations of length 100. So 1,000 qvecs and 1,000 ovecs. And each sequence will have length 100, and you'll store them in an array of size 1,000 by 100. Okay. Now then create 3 histograms for the values of O25. What is O25? O25 is the observation vector after 25 steps. So in fact, that's going to be the 25th row, it's going to be the 25th column of this matrix, right? Because O25 is the observation at the 25th step, O50 and O100, right? It says the histogram bar should add to 1,000, right? Because you're taking entries from 1,000 rows, so there should be 1,000 numbers for each of these. So if possible, put your histograms on the same axes, comment on your results. What do they show about the behavior of the model? Can you explain the behavior? Okay. And make histograms with separate bins for each state. So the histogram should have n bins, right? So if we have 30 states, you should have 30 bins. Now, I'll have to see what kind of results you get. We could actually generate many more sequences and get a better histogram. So we may end up doing that. Right? All right. So with the same sequences of observations as in 5, use the forward algorithm to compute the probabilities of O1 through O10 for the 1,000 sequences you observed. This will give you 1,000 probabilities. Now, these probabilities are going to be very small because there are many, many possibilities for one sequence of O1 through O10. Right? So these probabilities are going to be very small, but you can still create a histogram. Now, in this case, these probabilities are not going to be integers. They're going to be real numbers. But you should expect some very small real numbers. And it'll be interesting to look at this histogram of probabilities. So do the same thing for O1 through O12. Now, these probabilities will be even smaller, so you can't put these histograms on the same axes. Just so you'll make 3 separate histograms, one through O1 through O10, one for O1 through O12, and one for O1 through O14. Okay. So I'm doing a histogram of the probabilities themselves. So for each sequence, you compute a probability. Those probabilities themselves are going to have a probability distribution. And we want to comment on these probability distributions. All right, so that's the last one, and see what you can do with that.